In some earlier videos, we looked at the guess and check method for evaluating integrals. This time we're going to formalize that into a method called the method of substitution. And what it's built on is the idea of creating an intermediate variable, and that we're going to substitute into our integral. To see how this works, let's start off with an integral here, x cubed, the square root of x to the 4 plus 5 with respect to x. This is a complicated looking beast, but there's a claim that this is in fact the antiderivative. We're asked to show that. Keep in mind, if you're asked to show that an answer is correct, that an integral is correct, that's actually really easy. We just need to differentiate the antiderivative and see if we get back to the original function we started with. Well, let's do that. The derivative of this beast here is going to be 1/6. The plus c is not going to matter. It's going to have a derivative of 0. But the other part here, we're going to bring down the 3/2. So it's important to keep your derivatives versus integral rules together. Derivatives bring the power down front, copy the inside, and subtract 1 from the power, and then multiply by the derivative of the inside. So 4x cubed plus 0. All that together gives us a square root of x to the 4 plus 5. That's what the power 1/2 does. Then we have 3/12 is a quarter times 4x cubed, and oh look, those cancel. X cubed square root of x to the 4 plus 5. And that matches our original integrand. And if that's the case, we found the right answer. This is the antiderivative of the original function we started with. All right, so we know the answer here. The question is, could we have found a way to do this ourselves, a systematic way to go from this to this more complicated function on the right-hand side, not just by guessing? Notice how this structure here worked. We have this x cubed here from the derivative of the x to the 4 plus 5, or our inside function. This is inside a square root, but the derivative of that inside is what spat out something to do with an x cubed. Yes, the constants were off. We're never going to worry about constants because we can always tweak those. We're more worried about powers of x or any other functions of x, because they are the ones that complicate our integrals and derivatives. Another way to look at this is if we labeled this function here and called it g of x. This is essentially what we get for g prime of x. And so we have something and its derivative out front. That's going to give us the inspiration to maybe give this a short name and see if we can use that to simplify our integral. We're going to now try to tackle this from scratch, and knowing what the target is, it'll help. But we should have a method that works on anything that has this kind of derivative outside of the inside function. Let's see how that plays out. What we're going to do is create a new variable called w, and it's going to be our inside function, x to the 4 plus 5. We pick that because we see the derivative of w hiding out front. But let's work through some mechanics here. What we'd like to do is replace this part here with w. We can do that in one step. We'll need to replace this dx though. And so what we're going to do is take the derivative of w. dw dx will be the derivative of this, which will be 4x cubed. Now we're going to fall back on our earlier intuition that this is actually a ratio of changes in w to change in x, and so we can actually move these pieces separately. It takes a lot of theory to prove that this works in general, but for now, take it on faith. We can treat this dx as if it's a small unit of x. We're going to bring it to the other side, and we're actually going to introduce one more step here than we usually do. I'm also going to bring the 4x cubed down. So we're going to have 1 over 4x cubed dw is the same as dx. 18th century mathematicians like Euler would have loved this kind of notation. It's gone a little out of fashion since then, but it gives us a relationship for one of the parts of the integral. I can now replace the dx with the integral with respect to w. However, it's going to have this little multiplier because these are not quite the same. Rates of change are not quite the same. Changes in w and x at the same time. However, let's just do a mechanical replacement and see what we get. We're going to replace x's with w's and dx with dw's. How does that work? The integral of x cubed square root of x to the 4 plus 5 dx is equal to, we haven't replaced the x cubed yet. That wasn't our focus. Our focus is on the inside part here, and that just has the name of w, so square root of w. The dx we do have a replacement for. It is 1 over 4x cubed dw. Dx can be replaced with, swapped out for, that expression. And here we have a moment of greatness. Oh look, this x cubed and this x cubed cancel. What we've done is exchanged our integral that we started with, this complicated looking beast, by noticing that the inside was complicated but its derivative was lying there outside. This substitution process lets us divide by the derivative of the inside. So we got to divide by an x cubed and ended up canceling it in this expression here. And notice what we have now. We still have an integral to solve, but it is much, much, much simpler than the original. We've made major strides in getting a new integral, and in particular one that we can express pretty easily as a power, and then we can actually integrate this or find an antiderivative. We have a w to the 1/2. We know the rules that it is add 1 to the power, divide by the new power, and tack a constant on the end. Notice one little important element here. This is w's and these are w's. It only works if we have all one variable. Just like up here, this only makes sense if we have x's all the way through and no other variables. That's exactly what we have here. And if we do a half over that, we end up with 2 over 12, w to the 3/2, but w has a name in x's. W is x to the 4 plus 5. We want that to the 3/2 plus a constant, and lo and behold, if we tidy up the 2/12, we have exactly the answer we checked before, which is our inside function x to the 4 plus 5 to the power 3/2 and times a 1/6, which is a constant we might not have guessed at, but which falls out when we follow this method here of defining a new variable. There again is our solution, our integral value that we checked, and now we know it's correct, and now we've arrived at it straight from the original integral itself. That is an incredibly powerful technique for evaluating quite complicated looking integrals.